Hello everyone, myself Ms. Jayshree Patil from Fergusson College. I'll be conducting these sessions for physics. In 12th standard physics, there are 16 lessons, out of which the 5th lesson is oscillations. The weightage given to oscillation is of 7 marks as per the board pattern. So this is the first session of oscillations, in which we are going to learn the introductory part of oscillatory and vibratory motion. So let us begin the session with the help of presentation. Lesson number 5, oscillations, in which we are going to learn in detail about the oscillatory motion and the vibratory motion. In the earlier standard, we have learned different types of motions and the governing forces. Let us revise few types of motions. Rectilinear or translational motion, in which the body is moving along the straight line path under the action of the force, which can be observed in the adjacent figure. So here you can see that a block is kept on a table, and when the force is applied to it, then the block starts moving along the straight line path. Hence, the block is said to be performing translational or rectilinear motion. In circular motion, which may be uniform circular motion or non-uniform circular motion, the object is having a tendency to move along the circumference of a circle, which is governed by a centripetal force. So here in the diagram, it is observed that an object, especially a ball over here, is performing circular motion. On similar lines, one more motion is there which is studied in lesson number 1, that is the rotational motion. In this rotational motion, the object is moving about an axis of rotation, and the motion is governed by centripetal force called CPF as well as by the torque. So again in the diagram, it is observed that the rod is rotating in a horizontal plane, and the axis of rotation of the rod is perpendicular to the plane of the rod, and it is passing through its center. On similar lines now, a very important kind of motion we are going to introduce with, that is the oscillatory motion and the vibratory motion. When any object or a body or a particle is performing either to and fro motion or up and down motion or back and forth motion about a fixed point or a position, which is also called a mean position or equilibrium position, along a fixed path which is repeated in a fixed interval of time. This fixed interval of time is also called a periodic time or a period. Hence, the oscillatory or vibratory motion is to and fro motion of an object or a particle about a mean position along a fixed path which is repeated in a fixed interval called a periodic time. As an example, a string is fixed to the rigid support, and the other end of the string is being fixed to a spherical heavy ball called as the bob. So this is the assembly called simple pendulum. So initially, as per the diagram, the pendulum is at rest position, which is called a fixed position or a fixed point. So this position is called mean or equilibrium position. Now, why it is called a mean or equilibrium position? Because the forces are acting on the bob of the pendulum. One of the force acting on the bob along with a string is a tension along the string which is directed towards the point of suspension. The weight of the bob, say W, is acting in vertically downward direction. So at a fixed position or a mean position, these two forces are balanced with each other. Hence, the resultant force acting on the bob is zero. That is, no resultant force is acting on the bob. Hence, such a rest position of an object is called its mean position or equilibrium position. Now, if the bob of the pendulum is either stretched to left or right and released, then it starts performing to and fro motion about its mean position, which can be observed here in the animation. So the simple pendulum is said to be performing oscillatory motion along the fixed path. As we know, every motion is governed by a force. So over here, in case of oscillatory or vibratory motion, the motion is governed by the restoring force or the restoring torque, and this force or the torque only is responsible for a body to move back to its fixed position or mean position. As we know, the force is a vector quantity, so the magnitude of this restoring force is changing instant to instant and its direction changes periodically. So detailed study about this will be done in next couple of sessions. The examples of the oscillatory motion are oscillations of a swinging pendulum of a clock whose motion is similar to that of the simple pendulum. Next example is the oscillations of loaded spring. So over here, a spring is fixed to the rigid support and other end is free, which is fixed to a lightweight rectangular block. So when it is pulled down and released, then it starts performing up and down oscillations about its mean position. Similarly, the oscillations of motion of a needle of sewing machine is also one of the example of oscillatory motion. The examples of the vibratory motion are a vibrating tuning fork. So as per the diagram, these two parallel rod-like structures are called prongs of the tuning fork, and the lower part, which is called a base, that is called a stem of a tuning fork. So when these prongs are hit on a rubber pad, then the prongs of the tuning fork are set into vibration, which can be observed here on the screen. So like this way, a tuning fork is set into vibration. One more example is there of the vibratory motion, that is the vibrating string. In case of musical instruments, violin, sitar, if the stretch string is plucked anywhere and released, then the string starts performing the vibrations. These vibrations are passed on to the air molecules which are nearby to the string, and because of the vibrations of the air molecules, the propagation of the sound is possible and the pleasant sound can be heard. Now in this oscillatory motion and vibratory motion, there is a major difference. In oscillatory motion, the whole body undergoes oscillations, because of which frequency of oscillations is less. On the opposite hand, in case of vibratory motion, only a small part of a body is undergoing vibration, because of which the frequency of vibration is larger enough. Now here, in oscillatory motion, what we have learnt is the oscillatory or vibratory motion is taking place in a fixed interval of time, and that fixed interval of time is a periodic time. That means the oscillatory motion is periodic motion. Apart from oscillatory and vibratory motion, rotational motion, even a circular motion, is also periodic in nature. So let us understand now what is this periodic motion. Any motion which gets repeated after a definite interval of time is a periodic motion. Now, when any body is performing periodic motion, then it goes on repeating the same set of movements again and again, or we can say the body is performing same sets of movements in a fixed interval of time. The time taken for one such set of movements is called its period or periodic time, which is indicated by capital T. Example wise, the motion of Earth around the sun. So when the Earth is revolving around the sun, then the motion is a periodic motion, and the time taken by the Earth to complete one revolution is a periodic time, which is equal to 1 year or 365 days. Not only this example, even the hands of the clock, they are also performing a periodic motion. When the displacement of an object performing periodic motion is expressed in terms of trigonometric functions, especially either sine or cosine, then the same periodic motion is called as the harmonic motion. Now, as the sine and cosine functions are periodic as well as harmonic, that's why such periodic motions can be called as harmonic in nature. When any object is performing oscillatory motion, which is obviously a periodic motion, and the displacement in such case of oscillatory motion is expressed in terms of a single harmonic function such as x is equal to a sin omega t or x is equal to a cos omega t, then the oscillation is said to be harmonic oscillation. Example wise, here in the animation, it's observed that the motion is similar to the simple pendulum. So here the pendulum is getting displaced instant wise, and at the lower side the displacement versus time graph can be observed, which is either a sine curve or a cosine curve. Hence it is very clear that the simple pendulum, as observed in the diagram, is performing oscillatory motion which is harmonic in nature, because its displacement is either expressed as a sine function or a cosine function. But if the displacement in case of oscillation is a combination of two or more harmonic oscillations, that is, x is expressed as a sin omega t plus b sin 2 omega t, then obviously the oscillation is non-harmonic oscillation. So here on screen, the displacement equations which are observed are included with capital A, that capital A is standing for the amplitude of oscillations, and omega is standing for the angular frequency of oscillations. Over here, B also is standing for the amplitude of oscillations. The simplest type of oscillatory periodic motion is called as a simple harmonic motion, which is also called in short as SHM, which is a very, very important topic from oscillations. So what is this simple harmonic motion? More precisely, a harmonic oscillation of constant amplitude and single frequency is SHM. So in the earlier case, we have seen that whenever a oscillation is harmonic, then the amplitude of that oscillation has to be constant and the oscillations must be of single frequency. Depending upon the path of SHM, the SHM is classified into two categories. The first one is the linear SHM and the second one is the angular SHM. If the path of oscillations, that is SHM, is straight line, then the SHM is called linear SHM. On the opposite hand, if the path of oscillations is curved or circular, then the SHM is called as angular SHM. Let us start with now the linear SHM in detail. So to understand linear SHM, we'll check out the examples and the test for checking whether the object is performing linear SHM or not. So the test for SHM is that the force acting on the body must be in the form F is equal to minus Kx or F is equal to minus Ky, where K is standing for force constant or also called as the spring constant, and X or Y is the displacement of a body from its mean position. Again, this detailed study of F is equal to minus Kx will be done in the next session. Till that time, we have to keep in mind that for linear SHM, the restoring force acting on the body must be expressed as either minus Kx or minus Ky. The examples are oscillations of the loaded spring, oscillations of a simple pendulum, and oscillations of a liquid in a U tube. So let us begin with the first example, that is the oscillations of a spring. So this spring is also called as a spring mass oscillator because it is performing linear SHM. Hence, the system is either called spring mass system or spring mass oscillator. So consider a block, I'll say lightweight rectangular block, which is kept on a frictionless platform. One of the end of the flexible spring is fixed to a rigid support and the free end of the spring is fixed to a block as is observed on the screen. Now when the block is stretched to the right and released, then the block starts performing to and fro motion about a position which is called as the equilibrium position, and that is indicated by this vertical line. So here, when the block is stretched to the right and released, then at the same moment the force called restoring force acts into play, and that restoring force tries to bring the block towards its equilibrium position. So more is the force acting on the block, more is the displacement of the block. So here what happens is the position up till which the block is stretched and from that position it is released. That is called right extreme position. So after reaching to equilibrium position, the block doesn't stay there. Instead of that, it moves to the left hand side, and that left hand side is called a left extreme position. So block performs simple harmonic motion about the equilibrium position. So here from the animation it is very clear that the restoring force acting on the block tries to bring the block back to its equilibrium position, and that is proportional to the linear displacement of the block. So more is the force, more is the displacement of the block, and the negative sign over here indicates the direction, that is the restoring force over here as from the diagram is indicated by a red vector. So that red vector is directed towards the mean position, and the position that is standing for the displacement vector x, which is indicated by the blue vector over here, is directed away from mean position. So direction wise both restoring force and the displacement are oppositely directed. So here it is observed that F is proportional to minus x. Let us convert this proportionality into equality. That is F is equal to minus kx, where k is a force constant or a spring constant, which depends on the elastic properties of the spring as well as on the physical conditions, external conditions like temperature. When the force acts into play, then it accelerates the block towards the equilibrium position. Hence, the acceleration is given by force upon mass as per the Newton's second law. Hence, the acceleration, which is especially a linear acceleration, it's given by minus of k upon m into x. The bracketed quantity over here, which is the ratio k by m, is also a constant. Hence, here it is also proved that the linear acceleration of the block, that is also proportional to minus x. So, along with a force, the acceleration is also directly proportional to displacement, and both of these acceleration and force are opposite to displacement. So, here it is proved that the spring mass system or spring mass oscillator performs SHM along straight line path, which is called as the linear SHM. We'll study the positions separately. The first position is a stretched position of the block, which can be observed on the screen. The block is stretched to the right side. So this is the right extreme position of the block, in which the spring gets stretched. So because of the elastic properties of the spring exerts a restoring force on the block, and that restoring force tries to pull the block towards the equilibrium or mean position, which is indicated by this dotted line. So the force which is acting on the block is given by F is equal to minus kx, and it is directed towards the mean position, and the displacement is directed away from the mean position. So this is a diagram indicating right extreme position of the block. So from right extreme position, if it is released, then the restoring force is experienced by the block due to spring, which accelerates the block towards the mean position. So because of which what happens is the speed of the block goes on increasing, and the displacement of the block is going on decreasing. So because of this, the block returns back to equilibrium position. So here is the situation now. The block has returned back to its mean or equilibrium position. That's why over here the figure is indicating the equilibrium position, say A, that is a relaxed position of a spring mass system. Whenever a block is at its equilibrium or mean position, it is not experiencing any restoring force because the spring is at its relaxed position. So over here what happens is, because of the acceleration experienced by the block has reached to its mean position. But over here the speed of block has increased and it has become maximum at mean position. Hence the kinetic energy of the block is also becoming maximum, because of which it doesn't stay there and it moves towards the left extreme position, compressing the spring, which can be observed here on screen. So what happens over here is, the block is now moving towards the left extreme. So the motion of the block is retarded because of the restoring force. And because of this retardation, the speed of the block towards the left extreme position is going on decreasing and it becomes 0 the moment block reaches to left extreme position. Hence, at any of the extreme position, whether it is left or right, the displacement of the block becomes maximum, the force experienced by the block is maximum, the speed at the two extreme positions is 0. Now the motion is again repeated. Like this way, it is proved that the spring mass oscillator is performing linear SHM. In this session of oscillations, we have learned basic concepts of oscillatory or vibratory motion, even the examples of both these types of motions. After that, we have covered the harmonic motion. Then after that, what is linear SHM, what is angular SHM, and the example of spring mass oscillator in detail. Thank you.